Hello and welcome to the seventh lecture for our natural disasters course. In this lecture, we'll be looking at tsunami and how they differ from wind-caused waves. We'll discuss what causes tsunami and the nature of tsunami and mitigation efforts for tsunami. Interesting thing about the word tsunami, which is a Japanese word, tsu meaning harbor and nami wave, is that it's both a plural and singular noun at the same time. So a multiple tsunami does not have an S, right? So it's a singular tsunami or several tsunami. Prior to 2004, most people, or I should say a large number of people, may have been unfamiliar with what a tsunami was because a very large notable tsunami had not occurred for quite some time. Unfortunately, in December 26, 2004, that changed, where the large Sumatra Andaman earthquake, which we referenced when we were talking about earthquakes, occurred along the coast of the island of Sumatra, which is part of the country of Indonesia. That earthquake triggered a tsunami that swept through the Indian Ocean, hitting Asian and African shorelines. There was an estimated 245,000 deaths, probably higher. The seafloor west of Sumatra, it ruptured northward, for 1,200 kilometers over 7 minutes. So a massive segment of the fault ruptured. So a huge amount of energy was released in a magnitude 9.2 earthquake, and some of that energy was transmitted into the water, causing the tsunami. Now, by this energy, it's not the seismic waves. We'll see it's not the seismic waves. They're too high frequency to cause the tsunami. It's a much lower frequency, longer period movement of the Earth that causes a tsunami. And so this earthquake that caused a tsunami was the second largest in the last 100 years. And as I said, it occurred on the subduction zone where the Indian Australian plate subducts into the Asian plate. So in this image, we see the Indian Ocean and all the coastal countries that are shaded the darker orange are countries who were affected by the tsunami. So a large number of Indian Ocean coastal countries were impacted by this event. This is an image taken from Indonesia after the tsunami. You can see the coast is just pretty much wiped clean, all the infrastructure. This is a regional capital of the country of Indonesia, Banda Aceh. This is prior to December 26, 2004. This is the same location after December 26, 2004. So we see the destructive power of these tsunami. So as I said, tsunami is a Japanese word meaning harbor wave. They reach greater height whenever they enter a harbor or narrow space or even just shallower water. So an 8-meter high wave in the open coastline can transform into a 30-meter wave in a narrow harbor. And in Japan, 1896, an offshore earthquake shifted the seafloor, causing a tsunami to hit the coastline 20 minutes later. The highest waves were 29 meters tall in narrow inlets. Now keep in mind, a meter is roughly 3 feet. So 29 meters is a very tall, very large wave. 27,000 people were killed. The term tidal wave is sometimes used to describe tsunami, but that is a misnomer because tidal waves are actually waves that are caused by the tides, where tsunami are waves that are not caused by tides. They're caused by a sudden displacement of a large volume of water. Most of the time, that's the result of earthquake. So an earthquake has to be one in which the slip along the fault generates a vertical offset along the ocean floor. So, for example, a transform fault, which is strike-slip fault, I should say, where the motion is just purely horizontal as the rock slides past. the rock on the other side, that is not going to trigger a tsunami because there's no vertical movement. Where a dip slip fault, either a normal fault or a reverse fault, where you have the hanging wall or the footwall moving up or down, that is causing a vertical shift of the ocean floor and offsets the water mass above it. And that is what triggers the tsunami. Usually we have significant vertical fault motions along the reverse faults that occur along subduction zones. Most subduction zones are around the rim, not all, but most around the rim of the Pacific Ocean. So most tsunami occur in the Pacific Ocean. Not all, but most. 70,000 people were killed by 141 tsunami in the 20th century. So in a whole century, 100 years, 70,000 people were killed by 141 tsunami. Whereas one single tsunami, the Indian Sumatra Andaman, caused by Sumatra Andaman earthquake, the Indian Ocean tsunami on December 26, 2004, killed about 245,000 people in 13 countries. So you can see why I said most people would not be familiar, we're not familiar with the term tsunami prior to December 24th, because it had been a long time before since a large catastrophic tsunami occurred. Since December 26, 2004, we've had a second one, March 11th, 2011, the Tohoku earthquake off the coast of Japan, Sendai, Japan, triggered a tsunami that hit the coast of Japan. So the single event killed more than triple the number of people killed by 141 tsunamis in the 20th century, entire 20th century. So as I said, another very notable recent tsunami was the March 11th, 2011 Japanese tsunami. It was the result of fault rupture along the Japanese subduction zone, where the Pacific plate subducts under, it's interesting, I believe part of the North American plate there. So how does a subduction zone fault slip along a subduction zone fault trigger a tsunami? This illustration has the vertical motions exaggerated, but it does so in order to demonstrate how these tsunami are generated. So here we can see this oceanic plate is converging with the continental lithosphere of this plate, and the fault right here is locked together by friction. And as a result, the overriding plate is deformed. It undergoes that elastic deformation and accumulates elastic potential energy. And down here, you can see the time scale of elapsed time. So you can see we're on the order of hundreds of years it takes for this deformation to accumulate. See, actually, this island appears to be sinking because of this deformation. Now, eventually, friction is not going to be strong enough to hold this fault together anymore, and it's going to rupture. And as a result, this deformed rock on the overlying plate is going to undergo elastic rebound and return to its original shape. In order to do it, it's going to slide back up. And whenever it slides back up, it's going to displace the volume of water directly above it. And you see how that triggers the tsunami. So whereas wind waves, they are much smaller in scale, and a single wave is contained to half of the wavelength of the wave for wind waves, so it doesn't extend down to the bottom of the ocean. And wind waves, for that reason, their velocity depends on the period of the wave. So wind waves, they travel about 17 miles per hour for a wave of a 5-second period, and 70 miles per hour for a wave with a 20-second period. So the longer period waves or lower frequency waves, they travel faster. in general, that's longer wavelength waves. They travel faster. And so, however, tsunami, the entire water column is involved with the wave. And because of that, the speed or velocity of the wave is a function of the water depth. And the speed or the velocity v can be calculated by taking g, which is the acceleration due to gravity, multiplying it by d, the depth of the water, and then taking the square root. So get the so we have, oh, there it goes. So the velocity equals the square root of the acceleration due to gravity times the water depth. So what that kind of looks like, if this is speed, this is water depth, it kind of looks like that. So the deeper the water, the faster the wave, right? The shallower the water, the slower the wave. So for an average depth of 5,500 meters or 5.5 kilometers, that gives us a theoretical velocity of 232 meters per second, which is 518 miles per hour. However, actual observations of tsunami speed, they peak at about 420 to 480 miles per hour. The wave will slow as it approaches the shoreline because the water depth decreases. But these waves, they travel extremely fast and can cover large distances in very short periods of time in the open ocean where the water depth is very large. So the height of a tsunami, it changes according to water depth as well. A tsunami with approximately 1 meter height in open ocean can be 6 to 15 meters in the shallow water and even higher in narrow topography like a river inlet or a harbor. The wave height is the leading edge of a sheet of water that flows inland for minutes. And usually there's a series of waves, right? Waves, there's usually multiple waves. They're very long wavelengths, and they're separated by either 10 to 60 minutes. So either there's 10 minutes between crests or 60 minutes between crests. That means they range from periods of 10 to 60 minutes. So what that means is water would wash in, say if it's a 60-minute period, water would wash inland for 30 minutes, then it'd pull outward for 30 minutes. Then it'd begin to wash inland for 30 minutes and then pull outward for 30 minutes. So tsunami at the shoreline, they're not the gigantic version of a breaking wave. So let's say if this is the coast, they're not this giant version of a breaking wave that's portrayed in the movies. What a tsunami actually looks like, for such large wavelength that if this is the water, it's such large wavelength that whenever the tsunami makes landfall, it's almost as if the ocean just begins to flow inland. And so don't see this big crashing wave. You could see this large mound of water moving toward you, but what it really looks like is the ocean just begins to rapidly flow inland and it doesn't stop. If the trough of a tsunami makes landfall first, then the water pulls out rapidly, exposing the seafloor. Actually, on the coast of Sri Lanka, an island southeast of India, a trough made landfall along the coast there first, and the ocean pulled back, exposing the seafloor so rapidly, in fact, it left fish flopping on the exposed seafloor. Unknowing of the risk or hazard of tsunami, and that the sudden withdrawal of the sea being a sign of that, so people along the coast ran out to the exposed seabed to gather the fish, unknowing that the crest of the wave was following the trough. Right, so these look more like wind waves, right, where a tsunami is more just like a wall of water that comes flowing. Wind waves, they curl over and they crash, or tsunami is just water flowing inland. Just as I said, as the ocean just begins to flow out of the ocean and onto land. So an example of an earthquake caused tsunami in Chile, August 8th, 1868. A large earthquake shook the Arica in Bolivia, where several ships were moored in the harbor. Eyewitness accounts of rising sea. The second earthquake followed by a falling sea, as we mentioned, that can happen if the trough makes landfall first. Then a sudden massive wave hours later, which carries ships 2 miles inland. Another example was in Hilo, Hawaii, in April 1st, 1946. Large earthquake in the Aleutian Islands of Alaska created a tsunami that traveled across the Pacific. There was eyewitness accounts of a large hissing sound with advancing and retreating waves for several minutes. And then another tsunami in Oahu, Hawaii, March 9th, 1957. And there's a picture, you just see this advancing sheet of water. Well, that's the 1946. Here's the 1957 one. See the water just one photo, and the next photo, and the third photo, you can see the water just flowing in. So looking at the wavelength and the period versus height. So the destructive power of a tsunami is not due to its height, but it's due to the momentum of a large mass of water, with ultra long wavelength and period. So water is very heavy. Whenever it's moving, it has a lot of momentum, and it destroys almost anything in its path. Tsunami rushes inland for approximately 30 minutes before it pulls back out to form the next wave that washes in for 30 minutes. Long wavelengths and periods mean that the waves can bend around islands and hit all shores. So no shores are actually protected from the tsunami. So if you have a small island here and there's a tsunami traveling this direction, it's not only that only this coast is going to be affected, because it's such a long wavelength, the water rises in all directions inland as the crest of the wave travels through. So the whole coastline will be affected for an island due to long wavelength. And here you can see the very large speeds that tsunami travel with in the open ocean. So this was the wave fronts, or the leading edge of the tsunami, the 2011 Japanese tsunami. And here we have these thick white lines that shows us the wave front at certain time intervals after the earthquake. So here we have the 3 hour, pen back up. We have the 3 hour, interval there, the 6 hour here. By 9 hours, it made it this far. 12, 15, 18, 21. There's 22. And so you see the tsunami made it from off the coast of Japan to off the coast of Chile. So it pretty much traveled diagonally across the Pacific in less than 24 hours. So these waves can travel very fast in the open ocean. And so the cause of tsunami is anytime the water mass is hit with a massive jolt of energy, such as a vertical offset of the sea floor during an earthquake, the collapse of a volcano during an eruption, or a landslide, or mass movements, a large amount of rock or material slides into the sea from a coastline, or maybe the side of a volcano, or even meteorite impacts can trigger tsunami. So the biggest tsunami are actually caused by the rarest events, which are the impacts of large asteroids or comets. So the meteorite impact that brought about the Mesozoic mass extinction, which helped bring in the demise of the dinosaurs, it triggered a large tsunami that washed very far inland from North America, Central America, and South America at the time. Because that meteorite hit what is now pretty much the Gulf of Mexico, right at the tip of the Yucatan Peninsula in Mexico. So for earthquake-caused tsunami, as we said, it's fault movements along the seafloor. There must be vertical movement, resulting in the uplifting or downdropping of the seabed. And to have enough movement to generate a significant tsunami, the earthquake generally has to be at least a magnitude 7.5. So warnings of a tsunami include, well, first of all, you feel the earthquake. Second, you see the sea level draw down significantly if a trough is making landfall first. You can often hear the wave coming. Sounds like a freight train, some people say, or a large hissing sound. Any of those warnings, you want to seek higher ground immediately, go upstairs of a well-built building. And especially in the Pacific Ocean, they have warning systems. The first sensors were activated in 2003, and the warning system operates through the Tsunami Warning Center in Honolulu for the Pacific. And so there's buoys throughout the ocean. Now they're in the Atlantic and the Indian Ocean, and they monitor for tsunami to give warning. It's interesting, I said tsunami or not, they don't look like those large crashing waves, but even this sign is inaccurate as how it depicts the tsunami. So as we mentioned, there was an earthquake in the Aleutian Islands of Alaska, April 1st, 1946. So that's the Aleutian Islands are volcanic islands formed along the subduction zone. So there's a rupture of that subduction zone. It shook the Scotch Gap Lighthouse, which is steel reinforced concrete, 14 meters above the low water level. The earthquake did. 20 minutes after the second earthquake, 30-meter tsunami swept the lighthouse away. In this case, the first wave was the biggest. As we'll see, that's not always the case. The tsunami traveled across the Pacific, about 485 miles, slowing to 35 miles per hour near Hilo, Hawaii, rushed ashore and killed 159 people in Hilo, despite warnings. Thought that because it was April Fool's Day, people did not heed the warnings. Necessarily heed the warnings. May 22nd, 1960, a magnitude 9.5 subduction event, the largest earthquake ever recorded, created a large tsunami. 3 waves, each successively larger, hit the Chilean coast, killing 1,000 Chileans. Accurate warning was given in Hawaii, but still 61 people were killed. Tsunami continued to Japan, killing 185 people along the Japanese coast. And this tsunami could continue to be measured in the Pacific Ocean for a week. It was so large. So the water level across the Pacific Ocean along the coastlines was still moving up and down, in addition to the normal tidal fluctuations for a week. That's how much energy was imparted into the Pacific Ocean. And then the March 27, 1964, Alaskan earthquake, a 9.2 earthquake, killed 122 people on a very sparsely populated Alaskan coast. Triggered a tsunami that hit Vancouver Island and then California. So there was a series of waves. In this case, the 5th one was largest. Which wave in the series of waves that will be the largest is not predictable. It could be the 1st, it could be the 3rd, it could be the 5th in this case. So here you can see the wavefront contours, so how many hours where the wave was at different hours after the earthquake. For the 1964 Valdez earthquake in Alaska, there's those wave fronts. And then the 1960 Chilean earthquake, you can see those wave fronts as it traveled out. And so for the case of the Alaskan subduction zone, so this plate is subducting under this plate. Here is the subduction zone. So this area was moving downward and this area is moving up. Because as this was moving, this was being flexed down. So this region was was bending down, and this region was being pushed up. Whenever it slipped, it returns to its original shape, which maybe look like that, so which resulted in this moving up and this side moving down. And that large movement of the this land, this side moving down, up, and this side moving down, that generated the tsunami. As we mentioned, the December 26, 2004 Sumatra Andaman earthquake triggered a tsunami. It was this segment of the fault that ruptured and triggered a tsunami that traveled throughout the Indian Ocean. And then we mentioned the seismic hazard, the risk of a large, at least 9.0 earthquake occurring along the Cascadian subduction zone in the Pacific Northwest. Well, that earthquake will likely trigger a tsunami as well. So most killer tsunami are generated along subduction zones. All oceans have at least some short subduction zones. The Atlantic Ocean has the Puerto Rico Trench, which has had a magnitude 7.3 earthquake before. It also has the South Scotia Trench. But the 1918 earthquake, it triggered a tsunami or a submarine landslide and a 6-meter tsunami hitting Puerto Rico coast. British Columbia, which is this part of Canada, which is north of Washington State and Oregon coastlines, they've slipped in magnitude 9 earthquake in the past on January 26, 1700, which generated a massive tsunami. So this was 1700 was prehistoric time in this part of the country, but there is record of the tsunami, as we saw in our lecture about earthquakes in the geologic record, and also in the biological record in the trees being killed along the coast by being flooded, but there's also a record of it in the oral histories of the indigenous populations in this region. But also, there was a written record in Japan at this time, and the landfall of this tsunami on the Japanese coast was recorded. So this has happened. The last time a large earthquake happened along the subduction zone, it triggered a large tsunami. The next time, it's not a question of if, it's a question of when a large earthquake happens along this subduction zone, it's very likely to trigger another large tsunami, and it will be very deadly. We mentioned the 2011 Tohoku earthquake. It was caused by a magnitude 9.0 subduction zone earthquake off the coast of Japan. It's a very destructive earthquake. And this video, it shows how the tsunami makes landfall. It's not a giant wave hitting the coast, but it's almost like the ocean just flowing inward. It just keeps on flowing inward. This video is taken from the roof of a building along a river. So this is a river, and it opens to the ocean out here. So the coastline is in this direction. You see the water just flowing in, and the water height rises, rises, and rises. So here you can see the road. You can see cars that have been swept upriver. The water begins to wash over the road. Note the water level compared to the building with the green roof as time goes on. So this parking lot is currently exposed. Just give it a little while and you see how that changes. So this structure there is kind of acting as a dam. It's causing the cars to pile up against it. So now look, that green building, the water is almost completely up to the roof. Also, you may notice this other building off to the right, which you can't see right now. There's people on top of it as well. It's right there up in the upper right-hand corner. Now the building with the green roof has become detached from its foundation, and it's now moving. You can see a large fuel tank is floating up the river. Became detached. That's that white thing. Here's that building. It's now detaching. It's being carried away. You can see how all these structures in the back were just being washed away by the water. Now, the sheer amount of energy required to lift the ocean up, all this water up out of the ocean and flow inland, is a testament to how much energy is released by these earthquakes. That this is just a fraction of the energy, the amount that was transmitted into the water. Enough energy to lift the water up out of the ocean and flow inland like this. So those are earthquake-caused tsunami. But as we mentioned, other events can cause tsunami as well, including volcanoes. The eruption of Krakatoa, which we've referenced several times in our lecture about volcanism, its eruption in 1883 resulted in an extremely large volcanic eruption with volcanic masses flowing into the sea, creating a tsunami. The culmination of the eruption sequence was the collapse of the stratovolcano down into the partially emptied magma chamber, creating a extremely large 40-meter high tsunami. That tsunami washed and hit the shores of Indonesia, killing 36,000 people. Now, if this happened today, that number would be much higher because the population density is much higher than it was in 1883. And this landslide caused tsunami. So volcanic collapses. So this can occur even without an eruption because the flanks of a volcano sometimes slide because they are just alternating layers of rock or pyroclastic debris. And so deposits of slumps occur from whenever the side of a volcano slides into the ocean, or sometimes it's whenever the side of the volcano is actually even below the water, so it's a submarine landslide. In these slumps, the material can cover large areas of the seafloor and displace large volumes of water and trigger tsunami. So coastal areas to the southeast of Kilauea, down here, which is active volcano in the Big Island of Hawaii. It slides up to 25 centimeters per year into the ocean. If this would slide at once, it would create a tsunami 30-meter high directed to the southeast. Now there is a risk of tsunami in the Atlantic as well. As you said, there are some subduction zones. There's the Puerto Rican Trench, which is a small segment of subduction zone down here, just north of basically Venezuela. But there's volcanic islands such as the Canary Islands, the Azores, and Cape Verde Islands that could have flank collapses or submarine landslides that could trigger tsunami. So there are 3 Canary Islands have had mega collapses. The last one was 15,000 years ago. that triggered a tsunami that hit the coast of North America and South America, Europe and Asia as well. Next mega collapse could send a powerful tsunami to the coastlines of those four continents again. And models simulate a 10 to 20 meter tsunami traveling across the Atlantic. So flank collapses occur globally about once every 10,000 years. So even though there's not a significant amount of subduction zone in the Atlantic Ocean, because we do have some volcanic islands, we still have a tsunami hazard. In fact, at Rhode Island and Connecticut, in Massachusetts, they have tsunami warning systems. So these landslide-caused tsunamis, they can also be indirectly caused by earthquakes, because earthquakes can trigger landslides. So for example, in Newfoundland, Canada in 1929, there was a magnitude 7.2 earthquake off the shore that triggered a submarine landslide, which set off a tsunami. These waves arrived at the coast of Newfoundland 2.5 hours later. In Papua New Guinea in 1998, a magnitude 7.1 earthquake 20 kilometers offshore triggered an underwater landslide that caused a tsunami. It hit the coastline of Papua New Guinea about 5 minutes later, washing 4 villages on barrier beaches into the lagoon behind them. This causes us to rethink the tsunami threat. It's not caused just by large earthquakes, but it could be caused by landslides triggered by even moderate earthquakes. You can have a smaller earthquake that can trigger a landslide, and that landslide itself could generate a large tsunami. And then also, this can occur in bays or lakes. It doesn't have to occur in the ocean. For example, in Lituya Bay, in Alaska, July 1958, which was the largest historic wave run-up. That's how far the water washes inland. There was a magnitude 8 earthquake on the Fairweather Fault in Alaska, causing collapse of more than 900 meters of rock and ice into the bay. Triggered a tsunami. 3 large boats anchored in the bay, hit by a huge wall of water, 30 meters high, traveling faster than 100 miles per hour. The crews of the 2 boats, they survived being lifted and dropped by the wave, and it sent a surge of water 525 meters up the side of the bay. So because it was a confined waterway, the bay, that's why the energy was imparted to a small volume of water, so it created a large wave height. So here we see a table of notable tsunami, the date on the left, then the year, then the cause, the height, the site, and the number of deaths. So you see most of them are caused by earthquake, and if not earthquake, then we have subsea landslides. Then only 1, 2, 3 of them were caused by volcanic eruptions. So most notable tsunami are triggered by earthquakes, or maybe even sometimes indirectly through earthquakes and from landslides triggered by the earthquake. Now, seiches are another type of wave. They're not wind waves. It's an oscillating wave that's enclosed in a closed body of water, like a sea, bay, lake, or even sometimes even a swimming pool. So the energy from a strong wind or earthquakes can cause the water to basically slosh back and forth. That's what a seiche is, the water sloshing back and forth. So in Hebgen Lake in Montana in 1959, 2 faults in the lake shifted, and this caused the seiche, and eyewitness accounts saw the water migrating from one end to the other end of the lake over 11.5 hours. There was a strong winds caused water to pile up in one end of Lake Erie. And then once the wind subsided, the water was able to, was no longer being held against that edge of Lake Erie and was allowed to slosh back and forth. And so here we can see the water level record. The blue line's in Buffalo, New York at one end of Lake Erie. So Lake Erie is positioned. It's positioned like this, where Buffalo, New York is up here and Toledo, Ohio is down here. So 2 opposite ends. You see when the water level is higher in Buffalo, it was lower in Toledo. And when it was high in Toledo, it was low in Buffalo. And it was very high in Buffalo, very low in Toledo, and you can see it just alternating back and forth. So you see the water was basically sloshing it was sloshing back and forth within the lake. And that's a seiche. So what should you do if you feel an earthquake? Well, mild shaking for more than 25 seconds could indicate that a powerful distant earthquake may have occurred. And if you are along a coastline, then that earthquake was, especially a coastline with the subduction zone, that was likely a earthquake along the subduction zone under the ocean that may have generated a tsunami. So if you feel the earthquake, you should just automatically seek higher ground. The sea may withdraw significantly or may rise before the first big wave hits. The water may change character, make unusual sounds. All these are warning signs. So what you should do is abandon your belongings. Most lives are lost while trying to save possessions. Head for higher ground and stay there. If there's no higher ground nearby, then climb to the upper floor of a roof of a strong building. And if there's no sturdy buildings around, then climb a tree. If there's no trees, you see the level of desperation increasing, then grab onto something that floats. Use something as a raft. So here is a very impactful lesson to learn about the human component of natural disasters. So the December 26th Indian Ocean tsunami was extremely devastating as far as loss of life and property. And almost 250,000 people were killed. However, the closest inhabited land to the epicenter of the 9.2 earthquake was this island called Samuele Island. After the shaking stopped, the residents fled uphill immediately. And as a result, only 7 of the 75,000 inhabitants were killed. And they knew to do this because of an oral history that reminded them, when the ground shakes, run to the hills before giant waves arrive. So their oral history in their culture that was passed down through many generations, from the time that the last tsunami occurred in this region, which who knows when that was, it could have been hundreds of years, that saved those people's lives. Just that little piece of information saved so many lives. Where most of the people along the coast of the Indian Ocean had no idea of the threat of tsunami. So after the earthquake occurred, most people were trying to recover from the earthquake. They're looking for, loved ones. They're trying to recover. They're assessing the damage. They weren't moving inland because they were not made aware. There was not proper education of the people, and there wasn't proper action or mitigation put in place by the government to have, sirens, to have public announcements, and to have just general education that in the event of an earthquake, you need to move inland and seek higher ground due to the hazard or potential risk of a tsunami. And so many people along the coast of the Indian Ocean were killed just because they did not know to move inland. Whenever similar earthquakes occur in the Pacific, because the Pacific has a much larger track record with tsunami, they're much more aware of the hazard of tsunami. So they know if a large earthquake occurs to immediately move inland as fast as possible, move to higher ground, and that saves a lot of people's lives. So a lot of lives could say. So we have, here we have all those factors at play. We have the high population density along the southeastern Asian coasts, country coastlines. We have the low democracy index, which is likely the reason why they were not aware of the risks, right? They weren't properly educated of the risk of tsunami. And then the low GDPs, because of the developing economies, they didn't have the infrastructure or the resources to put in mitigation efforts. So, but But just that one island, Samuele Island, that one story saved so many lives, and it's so unfortunate that so many people died, just mainly due to for a lack of information. Because there was some time, especially in coastlines further away from Indonesia, to move inland if they knew that there was a tsunami. Plus, there was no tsunami warning system in the Indian Ocean. Why? Well, because a lot of those countries don't have the resources to develop the tsunami warning system. Since then, there's been an international effort to develop a tsunami warning system in the Indian Ocean. However, often the buoys are raided by pirates. They steal the valuable components of the buoys, such as copper, wires, and so forth, and render them, um, you know, I guess they don't work, so they go down often, and they need to be repaired. And so sometimes, um, I guess that causes a certain unreliability of the tsunami warning system. And once again, it's because of the economic instability and political instability of the region that you even have pirates in these waters because of the desperation of people. So Nicaragua, 1992, the subduction earthquake shifted the ground very slowly, creating little ground shaking, but transmitting energy into water very effectively generate large tsunami. So sometimes, even though very rarely, you can have a significant tsunami without ground shaking. So there are, we use coastal maps that map out the topography that gives us an idea of what the tsunami hazard zone is along the coastline of, because obviously the steeper the slope of the coastline, the shorter the distance the water will wash inland. So there's tsunami hazard maps of the Big Island, Hawaii, based on local topography. We have coastline mapping of now Indonesia, India, Sri Lanka after the 2004 tsunami occurred, and that mapping it actually indicated that areas where there was human activities actually increased the damage and loss of life. Human activities such as the removal of vegetation, like mangrove forests, reefs, those increase the impact of the waves because those reefs and mangrove forests are natural barriers that break up the wave and prevent it from washing as far inland. The coastlines of Washington, Oregon, they're mapped out, and there are tsunami hazard zones mapped there, so that in the case of a large earthquake, they know which regions need to be evacuated. And the same is true. They have the same thing for Chile, Peru, Japan, all these Pacific coastal countries. So how we have tsunami warning systems work is we have buoys and pressure sensors out in the ocean. So prior to 2004, NOAA operated 6 buoy warning systems in the Northern Pacific Ocean, and funding since then, since the Indian Ocean tsunami, has provided 32 additional buoys around the world, transmitting information to scientists. And so new tide gauge systems and seismometers along coastlines to also monitor tsunami. And how the warning system works is there's a pressure sensor at the bottom of the ocean. So as a wave goes by, the water pressure at the bottom of the ocean is a function of the water height. And so if a tsunami is passing by, if there's a large wave, the water pressure will be anomalously high because the water height above there will be, so there is normal fluctuations to the water height, and that's caused by the tides. But whenever they see a large increase in water height, which you can just convert water pressure to water height, if you know the density of water, if there's an enormously high water height above a sensor, that's indicative of a potential tsunami. And so how the sensor works, it telemeters, which uses acoustic waves, sound waves, transmit the information of the water height to a buoy. The buoy then converts the acoustic signal into a radio signal. By radio waves, it communicates with the satellite, and the satellite then communicates with the Tsunami Warning Center. So that's how the information is relayed from the sea floor to a buoy, to the satellite, to the Tsunami Warning Center. And they are monitoring basically the water height in these different areas of the ocean. And whenever a potential wave is recorded, then they pay closer attention to determine if it actually is a tsunami. It could be a rogue wave, for example. But if it is a tsunami, then they are able to record its direction whenever it determines direction, whenever it arrives at other buoys. And once they know its direction, they can issue warnings. And so it's crucial to have the tsunami warning system, especially if it's a coastline that's far enough away from the earthquake that they might not feel the earthquake. They still could be impacted by the tsunami once it reaches their shores. So that concludes our lecture on tsunami. Thank you very much.